We first study mining spatial associations. Spatial association or spatial frequent pattern share some commonalities as a general association and frequent patterns. For example, the association rules are also in the form of A implies B with certain support and confidence. In this context, A and B could be sets of spatial or non-spatial predicates. The spatial predicates may indicate topological relations or spatial orientations or distant information like close to, within certain distance. And the measures support and confidence are very similar to the general ones. The rules we can find could be like if X is a large town and X intersects with the highway, then X is likely to be adjacent to water, like lakes and rivers and ocean, so that with certain support and confidence. In spatial data mining, quite often we would like to explore spatial autocorrelation. That means spatial data tends to be highly self-correlated. Nearby things are more related than the remote things. For example, when we study neighborhood, study temperature, likely we pay more attention to find interesting relationship in the nearby objects. In spatial association mining, there's an interesting heuristic called progressive refinement. The general philosophy is this. For spatial relationship, there are some rough ones like close to, which is generalization of some more refined one like nearby, touch, intersect, contain. They are somewhat all close to. Just give you an example, like here, you can see near highway intersection, you may be able to find shopping centers and gas stations. But how close to, whether they are very nearby or they are almost touch the highway intersection. So in that sense, those are detailed, refined relationships. However, if we first find those close to, they are frequent together, okay, then if we want to find it more refined, how close to are they really to the intersection? So we can say if the close to is a frequent pattern, then we are going to study the more refined ones. To that extent, this is the philosophy of progressive refinement. That means we first search for rough relationships and then refine to study more refined relationships. The general philosophy is if the rough relationship is not frequent, so there's no need to study the very refined one because they are not frequent as well. Okay. So to that extent, we can do two-step mining of spatial association. The first step is we use reasonably cheap or low-cost algorithm like minimum bounding rectangle or R-trace for some rough pattern mining. That means we first compute the rough spatial frequent patterns. Then we know if the rough one is frequent, then we are going to get into refinement process. That means we may study more detailed algorithm using more refined data structure. So this principle can save a lot of mining cost because we first using rough ones, we get a big filter a lot of unnecessary pairs because they are not frequent already. We don't have to refine them. Okay, we don't have to use a refined method to study more refined patterns. We will discuss mining spatial colocation patterns. What is spatial colocation pattern? Usually, a group of spatial features or events can be frequently collocated in the same region. For example, West Nile virus may often occur in the regions with a poor mosquito control and the presence of birds. So if we can find such patterns, we may have better way to control the spread of the virus. Let's look at the example on the right. So we have A, B, C, D as 4 types of objects. You can think A could be West Nile virus, spreading region. B could be some mosquito region, or C could be in some cities. D could be the presence of birds, something. Okay. Then we use the edges, means they are co-located. For example, 3, 6, 17 are co-located. We use edge, link them together. And 4, 7, 10, 16 are co-located together. We use the edges, linking them together. Okay, like 2, 9 could be co-located, but on the other hand, 2, 14, 18, 11, and 15, these are co-located regions. Okay. Then we may be able to find row set. The row set means this. Okay, if we want to find A, B, C, D, how many objects are co-located together as A, B, C, D for types? We may be able to find 4, 7, 10, 16 are co-located, and 2, 11, 14, 15 are co-located, or 8, 11, 14, 15 are co-located. That means A, B, C, D, we may find actually 3 instances they are co-located. That's their row set. On the other hand, A, B may be a little more. For example, 5, 13 is co-located, 7, 10 is co-located. So we may find more, instances. Then we may get a co-location rule like this. If pattern A is co-located, whether pattern B are also co-located, we may find this conditional probability of the co-location patterns. That means if we want to find AB may imply CD. That means if AB are co-located, likely CD will be co-located with certain, probability. Then we need to compute the pattern A at what condition and how many cases when A is there and AB is also there. That means actually AB, the cases essentially is the case. You can find A and in the row AB row set. Okay. Essentially what we need to calculate is ABCD is a row set. You probably can see there are 3 such cases ABCD together, but there are 4 cases AB together. So the condition, if you find AB, then you find a CD are co-located, then the condition actually 3 over 4 is 75%. That means the conditional probability for this rule is 75%. Then the interesting thing is, can we find such co-location patterns and rules automatically and efficiently? Okay. So let's see how we can derive efficient algorithm to find them. Okay. To find efficient algorithms, we first introduce another concept called participation ratio. Okay. That means that the feature F is participating in this pattern C. What's the probability? Okay. So for example, A participating in ABCD, you can see A is a red one. We have 1, 2, 3, 4, 5 cases you find A. But we only, every time we find A, we can find A, B, C, D. There are only 2 such cases, like 7 and 14. That's why we get a 2 over 5 is the participation ratio. Similarly, if you want to find D participating in ABCD, D actually is the blue circle. You can see there are only 2 blue circles, but both of them is completely participating in this ABCD pattern. That simply says you get cases 2 over 2 is 100%. Then we may derive an interesting property called monotonicity property of participation ratio. Okay. That means suppose we have C and C prime as two colocation patterns, but C prime is a subset of C. Okay. Then for every feature F, if feature is participating in C prime, okay, then the probability will be higher than participating in a superset. This is quite easily can be easily understood because you can think about this. If A participating in AB, okay, then the chance is higher than A participating into in ABCD, because every time when AB occurs, ABCD also will be there. When ABCD occurs, AB will also be there. That's why when F participating in C, for sure the probability or the participation ratio will be higher than participating in its superset. So based on these monotonicity, we can work out an a priori-like algorithm to efficiently mine colocation patterns. Let's give such an example. Suppose minimum feature support is rewritten as sigma, and the minimum participation ratio is rewritten as rho. Then we start from a set of single feature patterns. If they are frequent, that means if their support is no less than sigma, okay, then we can keep using a priori like a principle to find their pairs. That means from the single feature pattern, try to find 2 feature patterns, 3 feature patterns, grow up to size k. Anytime we can stop if the pattern is not frequent anymore, because once it's not frequent, its super pattern will not be frequent. This is simply based on the a priori principle. Then based on these participation ratio monotonicity, we will be able to find all the super patterns of a single feature or the multiple features. Suppose we get a feature is P, we want to find its super feature, okay, or super pattern. And we know we can get a little bigger super pattern to see whether it's greater than rho. Anytime if it's not greater than rho, its super pattern will not need to be examined because they cannot be bigger than rho anymore. So based on this a priori principle, we can easily work out efficient algorithms. So that's the trick, or that's the interestingness. If we can find a monotonicity pattern, we will be able to work out, a priori-like efficient processing algorithm. In this unit, we are going to study mining and aggregating patterns over multiple trajectories. When we study spatial and temporal patterns, an important pattern is trajectory pattern. That means you look at the points, the objects, they moving along the spatial, in the spatial map along with time. So we call these are the trajectories. What we want to find are trajectory patterns. One interesting trajectory pattern mining method called partition-based trajectory pattern mining. They are mining T patterns. T means trajectory. This is a work done by a group of Italian researchers. They published in KDD 2007 called trajectory pattern mining. Their mining method essentially is really good on study like busy traffic in a city. You can think a city can be partitioned into equal weight grids to obtain regions of interest. For example, one grid may represent the museum, the other grid may represent a railway or campus. Okay. Then when you study the busy traffic they go along the route, you will be able to find at what hours or how much time you will find a very busy traffic and how long it may take to reach the other side. Okay. So what we can do is we can transform each input trajectory into a time annotated symbolic sequence. For example, you may transform one location is a railway station, another location is Castle Square, the third location could be museum. And based on the time, you may say, from the railway station, it takes about 15 minutes to reach Castle Square, then it takes 2 hours and 15 minutes to reach museum. And we can use a constraint-based sequential pattern mining because each grid is matched into a symbolic sequence. So finally, you can use the symbolic sequence to represent the whole trajectory and try to find trajectory pattern is trying to use constraint-based sequential pattern mining. The constraints can be the range of time delay. Then the constraint-based sequential pattern mining results can be mapped onto the map to show, how much time it may take from one location going to the other location. That kind of matching T pattern will be something like x0, y0. After alpha time delay, you will reach x1, y1 points. This will get into explicit representation of the patterns. Then another interesting group of studies are detecting moving object clusters. That means you may think trucks, you may think animals, they are moving together. You may want to find their moving object clusters in this sense. Okay. The first one definition is flock. Both flock and convoy require k consecutive timestamp in order to find patterns. The flock essentially is they require at least m entities are within the circular region of radius r, and they are moving together in the same direction. Then we call these the flock pattern. But the flock pattern is a little too rigid in the sense they require at least m entities moving in k consecutive timestamps, and it's within their movement are within the circular region of radius r, their relative distances. Okay. And sometimes this radius r is too rigid. Then convoy definition is using density-based clustering. They don't have to be within radius r. They can be tighter or they can be a little looser. As long as they form a density-based clustering, you will be able to find those m entities. And in the k consecutive timestamps they move together, you can think they are convoy patterns. However, such movement constraints are still very rigid in the sense both require k consecutive timestamps. We may think like animal movements, at certain timestamp, the animal may not be so closely clustered together. They may spread around to graze or to do other things. In that sense, we may relax this k consecutive timestamps to allow at certain timestamps, they probably are quite far apart. But on the other timestamps, you will be able to find they are very closely moving together. Okay. In that sense, we define such pattern as swarm. Swarm means the moving objects may not need to be close together all the consecutive timestamps. Okay. Of course, to find such movement pattern, it will be more costly than finding flocks and convoys because the pattern is more relaxed. Some efficient algorithm has been developed to mine such pattern. The paper was published in VRDB 2010. Now we look at another trajectory pattern is doing clustering, try to find them. We call trajectory clustering. This could be useful in, for example, try to forecast hurricane landfall. If you overlay many years hurricane together, you may find they may form very close clusters. However, if you try to take the whole hurricane path as inseparable, you will not be able to find such patterns, just because at certain points of time, these hurricanes may overlay nicely, but at other time, they may become more spreading because they were, influenced by different flow of the air. Okay. So try to find such patterns. We will propose a partitioning and a grouping approach. Partitioning means you first chop these trajectories. For each trajectory, you chop them into a sequence of segments. Okay. Then, after chopping these into sequence of segments, you will be able to find for certain fragments, they are moving in the same direction, they may form nice patterns. You can group them together as trajectory clusters. Then, how we can nicely find such patterns? For partitioning, you can use minimum description length principle, called MDL. Okay. The MDL, the general philosophy, is you try to use minimum number of points, but maximally reflect the trajectory, the real trajectory path. That means instead of thinking you use many small fragments, which are too costly, you try to use less of them, but you don't want to use too few because you will distort the picture. You will try to maximally approximate the real trajectory path. Okay. In that sense, you may say I use minimum description length principle. When the trajectory started turning in the sharper angle, I will try to say this should be a separate points. Then you may find smaller number of fragments, but maximum, preserve the shape of the trajectory. So this is an interesting algorithm published in Sigma 2007 called Trajectory Clustering, a Partition, and a Group Framework. Now we study another interesting movement pattern called mining semantics-rich movement patterns. We'll first see what is a frequent movement pattern. Okay. Frequent movement pattern is movement sequence frequently appears in the input trajectory database, but we care more on the semantics here. For example, from home to Starbucks to office. So maybe the home may be different, or office may be different locations, but this pattern may be interesting. Even we can consider the home and office could be just the same semantic units in different locations. So comparing to frequent movement pattern versus frequent sequential pattern, we can say they both are at finding frequent subsequences from input sequence database. However, for mining frequent movement patterns, we would like to think of similar places may need to be grouped together collectively to form frequent subsequences from the semantic point of view. Now we look at mining semantic-rich movement patterns. The semantic-rich movement pattern means in addition to know how people move from one region to another, we want to also understand the function of the regions. That means we want to see people moving from office to restaurant or from home to gym. So we promote a two-step top-down mining approach. The first step is try to find a set of coarse patterns that reflects people's semantic level transitions. That means as long as a region carries the similar semantic functions, we may want to consider they are the same function or same entity. Then we, in the step 2, will split each course pattern into several fine-grained ones by grouping similar movement snippets together. This time, we'll consider spatial temporal. Besides semantics, we're going to consider spatial and temporal features more seriously. A recent study published in VRDB 2014 called Splitter, Mining Fine-Grained Sequential Patterns in Semantic Trajectories, is an interesting study in this direction. Now we study another interesting issue called mining periodic movement patterns. Usually, the sensor may register movement data, but in many cases, you may have very sparse data. Just giving you a very interesting example. For example, animal scientists, bird scientists, they would like to study animal movements and bird movements. They put sensors on the body of those animals. But remember, the sensor usually is pretty small. On the other hand, it will need to be last for a long time. Like for study bird migration, a sensor on the body of the bird is expected to last for a year. Okay. So how could a sensor could be lasting for a year without charging the battery? Okay. The only thing you can think is we will get a very sparse data. Like 24 hours, we may only register one GPS location. Although 24 hours, the bird may fly very far away. Okay. Then if we want to find a periodicity, the interesting thing could be it's very hard to find the periodicity if there's no overlap, just because the data is so sparse. Then just look at how to thinking about bird flying patterns. Okay. We just think the bird, suppose this place is a nest of the bird. Okay. Then if you just look at the bird, how they exactly fly with a very sparse sensor data, you will not be able to find any meaningful periodic patterns of bird flying. However, you may find every night, every evening, the birds were flying back to the nest. In the morning, it will fly out from the nest. So from the nest point of view, or from the cluster center point of view, it does have some periodicity. Okay. Then we may take such location as our reference spots. That means the reference spots can be detected using density-based method because they come back, quite frequently. Okay. Then with this, if we do just based on the nest, we say when they are in the nest, when they are out of the nest. So we will be able to find nice and interesting periodic patterns. That means the periodicity is more obvious when we look at the binary sequence, like in and out of the nest. So that's an interesting one. You can see if we only think about the nest, the periodicity will be able to be detected for each reference spot using Fourier transform and autocorrelation. Now we look at an interesting example on mining periodic patterns with sparse data. So this is a real data set about birds fly in North America. Okay. So this actually accumulates 3-year bird migration data. They are very, very sparse. However, if you, based on the dense points, you take those dense regions as reference spots, you will be able to find a periodicity because in the winter, they're going to fly down to the south. In the summer, they may fly back to the north. In the middle, they may fly some places to have some other activities. So you will find a few interesting reference spots. Once we detect periodicity based on those reference points, we will be able to summarize such patterns in a periodic way because we find a period and we find the nice periodic patterns. So this is an interesting study based on the very sparse data. We will be able to mine periodic behaviors for moving objects. Then the previous study, we will assume there's like the periodicity can be detected because the period is sort of known. Okay. Then in many cases, the time-related data can be scattered and sparse. For example, phone calls at a location, it could be very sparse. And then for such sparse data, if we look at the time, we will be able to map the calling time in the sequence based on the time. You will say 5, 13, 18, 26, 29. If you map this, into the time sequence, it's very hard to find a periodicity. Okay. Then what about if we can guess a right period, like t? If t is 20, if we guess it right, you probably can easily see they form a very dense cluster. Okay. However, if you got a wrong guess on the period, likely these mapping will be scattered along the whole period. Okay. So that means the projection on the true period, it will show a highly skewed cluster distribution. Based on this observation, some in-depth study and algorithm has been developed to detect the true pattern and mining event periodicity from incomplete observations. So in this whole session, we discussed a few interesting issues. We studied mining spatial associations, mining spatial colocation patterns, mining and aggregating patterns over multiple trajectories, mining semantics-rich movement patterns, and mining periodic movement patterns. In this session, we actually used the following research papers. If you would like to know more, we strongly encourage you to read those research papers. Thank you.